Okay, thank you very much. And well, as the conference started off being theological, very early on, I decided I'd ask a theological question, which is, what is the purpose of doing things? I thought I should sort of try and work through reasons for doing things. Anyway, this is joint work with Galia Al-Hamzi and Shan Majid. And, well, yes, we've been here before, I guess, but we may as well just go through it for the sake of it. So for a possibly non-commutative algebra, differential calculus, graded algebra, a derivation, well, signed derivation, A and D of A generate the whole differential calculus, and the star conditions, which haven't quite been so much used, but which basically reverse order again in a signed fashion. And I'll want to take covariant derivatives, but I want to think of modules over, well, the algebras and algebra functions on a manifold. And if I have a bundle, I can take sections, and the formula at the bottom gives a right connection in terms of standard differential geometric sections and local coordinates dxi. And up at the top, we've got the more usual, well, more inclusive, non-commutative formulation of having a connection in terms of the Leibniz rule. And I do want to say something about bimodule covariant derivatives, but I wonder, part of what I want to do is to try and say why I want to say something about these. Now, the other thing is that these things are mixed. Now, that means we have a bicategory. Okay. So if I've got algebras A, B, and C, E is an A-B bimodule, F is a B-C bimodule, and E tensor F is then an AC bimodule. And I can change E into G, and then I can change this into another bimodule. Now, what I've done here is this, instead of MAA, which is a bimodule, well, basically bimodules over a single algebra, I've just got M, which is a colored monoidal category. The monoidal category consists of lines representing the bimodules. I color the regions in between them. That represents algebras, and I've got little boxes here, or combinations of lines which represent bimodule maps. And, I said bicategory. If I wanted a bicategory, then my algebras would be objects. My bimodules would be morphisms between the objects, one morphisms, and the bimodule maps would be two morphisms, that is morphisms between the one morphisms. Anyway, okay, so much for two categories. We're going to work with this thing. So, right, well, if we at least temporarily fix right covariant derivatives, we then ask for a modified left Leibniz rule, as you've seen before. But as it appears sigma halfway down, you see it goes from A omega 1A tensor E to E tensor omega 1B. So it's going to mix up the differential calculi. And one of the nice reasons for this, I want to try and present other nice reasons for this, is that we can then have formulae giving a tensor product of bimodule connections. And there are a large list of people who worked on this from, well, really quite a long time ago in the physics literature and places like that at the bottom. And if I've got a module map, then I can differentiate that just by applying a covariant, well, basically by commuting it with covariant derivatives. And that will make a brief appearance later on. But now, I need to convince you that positive maps are really easy. Well, what is a positive map? Well, if I take a map, just a map between the topological space of a circle and circle, and I have a positive function on here, and I apply the map, well, actually, I guess it should probably be a pullback the other way, never mind. Then I get another positive map. So the idea is that, well, certainly if I have a star algebra map between C star algebras, it preserves positivity. By definition, on a C star algebra, positive elements are of the form A star A. And if I apply a star algebra map to that, I get something of the same form. So what I want to look at are maps which preserve positivity, but in fact, it's a lot easier if I actually say that it preserves positivity when applied to matrices, because there is an incredibly nice description of such things. Okay. So let's take a Hilbert space. And on the Hilbert space, I'll have my algebra A, which is going to act on the left on the Hilbert space. And if I take an element of the Hilbert space, then I can define phi of A as being the inner product with H with AH. And if this is a standard Hilbert space inner product, please don't object if I put a bar on that. It's just to indicate it's actually, that's where the conjugations happen. This is all a complex inner product. Then this will give a positive map. And that's the whole idea of the GNS representation of states. Now, but suppose that my inner product actually takes values in another algebra, and that it is positive in the sense that if I take the inner product of something with itself, then I end up with an element which is greater than or equal to 0, which is positive. Then what I have is, well, a positive inner product and an action of A. And this is going to give me, well, if I complete it suitably, then it's going to give me a Hilbert C star bimodule. And what I want to do is to convince you that this is all an awful lot easier, and I've just probably convinced you that it is. Okay. So let's take functions on a circle. So Z is just E to the I theta, standard complex variable on the unit circle. Now, if I've got two functions, f and g, on the circle, then I can define their inner product just to be the complex conjugate of f times g. And that, if I apply that to f, then I just get norm f squared, and that's certainly positive valued. So this is going to be a positive inner product on the circle. Now, it's also a right module for multiplying by the algebra of functions on the circle. So here, here I want to take B to be functions on the circle, and so far E will be a right B module, and this will have well, a positive inner product. Now I'm going to take lots of circles. I'm going to take a circle for every natural number, and I'm going to get this inner product here. So the n and the m are just indexing different circles, and the different circles are all orthogonal, and the s and the k are just telling me in the Fourier decomposition or Taylor series which power of z I have. So that's all terribly positive as well, because the sum of positive things is positive. Now, however, the cunning thing is what happens at the bottom, because I haven't told you what the algebra acting here is. It's got A, B, and well, A star and C star are, yes, yes, A, B, C, and D, satisfyingly, well, and it's a representation of quantum SU2. And it was written down by Voronovich ages ago. In fact, this is where the compact quantum group thing started. And if you wondered where the condition on what real values Q can have to be a C-star algebra, that gives you them. Except Voronovich just had an ordinary complex number valued inner product. We've just added the circle thing just because we can. So what this gives is it gives an inner product, a positive inner product, taking values in the circle for representations of quantum SU2. Now, if I choose E in that representation, then the formula phi of E is equal to the inner product of AE just with the original E. That will give a positive, a completely positive function from quantum SU2 to functions on the circle. So, okay, well, we've just constructed a terribly non-trivial, completely positive map for absolutely any element of that representation. Now, what would I like to be true about that positive map? Well, I'd like it to be differentiable. I haven't actually told you how a positive map can be differentiable. Okay, well, actually, let's just go through why do we want completely positive maps? Well, it's a really standard thing in the theory of C-star algebras that there are not enough algebra maps to go around. For loads of purposes, K theory, KK theory, anyway. Basically, there's an industry of people developing alternatives to algebra maps, and completely positive maps are a really good alternative. We're going to be looking at dynamics of these things. Now, one of the things in noncommutative geometry is, well, in C-star algebras, you've got lots of C-star algebras which are linked to groups and dynamical systems, but more generally in noncommutative geometry, we expect symmetries to be Hopf algebras rather than groups, and an element of a Hopf algebra will not, in general, give you an algebra automorphism because it doesn't have the right coproduct. Now, I'm not going to tell you about the spectral sequences that you can get out of this. Let's brush that bit under the carpet. But differentiable. Okay, if you open a textbook on algebraic topology and you say, what does it mean for a map to be differentiable? What they will tell you is a cochain map. So if I have let's have a de Rham complex, well, any complex, whatever, particular de Rham complex for A, and let's have a de Rham complex for B. The idea is that a map here is differentiable if it, well, basically, if you can have an extension of that map to all degrees in the Durham complex in such a way that it commutes with the D's. And this is a terribly good definition for algebraic topology. Now, what we want to do is to do this, but we have to remember that our positive map is defined by an inner product. So we have to differentiate an inner product. Now, if you look at something like Riemannian geometry, the standard way to differentiate an inner product is to use a connection on the module. Okay, so we use a connection on the module. Now, because this is a permission, it's got a conjugate in there, we only actually need a one-sided connection. A right connection is perfectly good to do this job of differentiating the inner product. So if we differentiate this, then we'll again, brushing under the carpet for what the formula on E bar is. We've got d phi of E involves nabla of AE, where A is the wrong way round to use the ordinary Leibniz rule. I want this to equal phi 1 of dA if this is going to give me a cochain map. So I want to make a formula differentiating this to give me a formula in dA. Well, that is the bimodule derivative. This is sigma of dA tensor E plus, and then there's the A times nabla E. And the A times nabla E, I'd really prefer not to have. I mean, it will mess my formulae up. So I will put a condition on which, because I don't want things to become too messy, just to get a cochain map, I'll say that I want to find E, defining my positive map, which has the property that nabla E is equal to 0, because then I can write down what phi 1 is equal to. And phi 1 for a one-form xi is precisely given by the sigma for the bimodule connection and this inner product. And we've now got the first lot, well, the first square which we require for our mission in algebraic topology. Now, if we want to keep on going, then what we can do is, well, basically, there are ways to just extend sigma up to 2 forms, 3 forms, and so on. And you require a condition on the curvature of the connection. And you also, to make things nice, really want a maximal prolongation calculus. You've heard that one. You've heard that before, much earlier in the week as well. A condition on A. So, well, we could have a little bit of fun with this and take a state evaluation map. Okay, matrices. Now, the pure states, the boundary of the convex set of all states. The state is just a complex valued positive map normalized so that phi of 1 is equal to 1. So this is the choice showed that the pure states on the matrices are essentially CPN, well, CPN minus 1. And if we do a small amount of messing around, we can find what the corresponding Hilbert C star module for that is. It's actually the column matrices tensor product continuous sections of the tautological bundle on CPN minus 1, which just means at any point that ray, well, you have the ray in the row matrices, the row vectors corresponding to the point where you're at in CPN minus 1. And if we go through the calculation, then we can choose a suitable connection to make this differentiable. Remember, we need this condition. for our particular value of E, which I've given up there. And if we use the holomorphic D-bar calculus on CPN -1, then you get this nice formula where I've used a standard representation for this of a fully higher dimensional universal enveloping algebra. Okay, so I said dynamics, didn't I? Right. So what I want is a map into, well, I want B to be equal to the functions on R. Because if I want dynamics, I want variation in R. If I've got a function which takes values in R, I can put in my value of time. I'll have a time parameter t here. I put in t equals whatever I evaluate this. I can move states around the algebra. And what I want to look at is the A times, is the left A, right C of R, well, C infinity of R, whatever, module, well, let's just take the tensor product by the KSGNS construction. That's good enough. So the nice thing, well, what's our connection going to be? Well, there are lots of connections, but if I want this to be differentiable, I know that I want to have a bimodule connection. Now, bimodule connections means I have a sigma. Sigmas are much easier to find than connections because they've got much stronger, well, basically sigmas are a bimodule map. So what I have is I can then define, well, the sigma gives me a vector field on the calculus for A, a vector field being an element of the dual of omega 1. And then I can work out what the connection is, and again, because I want this to be differentiable, I want to solve nabla E equals 0. And that gives me that differential equation. And that differential equation is a differential equation for the time variation of an element of that bimodule. And that bimodule will then give me a state varying in time on whatever the algebra A was in the first place. Oh, except I haven't told you the condition on that connection actually preserving inner product. That condition is a reality condition. So in equation 6, now, given a one form omega, you can take it star for a star algebra. And if I demand, okay, now I'm going to have a reference state on A, which for a Hopf algebra in a moment is just going to be the Haar integral. But what I need to do is I want to solve these conditions, and I'll need X to be real, and I will need kappa to be the divergence of X. Okay, so if we keep on following this, we're now forced to consider real vector fields and divergence of vector fields. Now, there are two ways of defining a divergence of a vector field. You can either define a divergence of a vector field by doing integrals by doing integration by parts, or you can define it using a connection on the vector field and then contracting the connection. And for a Riemannian manifold, these give exactly the same thing, and we can insist that these things are again the same thing, and we get a lot of material on stars of vector fields, which okay, let's go here. Now suppose that I did this construction for a Hopf algebra. And I start off using an inner product, which is just given by the Haar state. Now, what you have is a vector field which is giving a velocity flow on a noncommutative manifold. Into that is coming this complicating factor that we've got a divergence of that has to come into the equations as well. But okay, if we had a Lie group, what would we do? We'd take a left invariant vector field and we want to integrate it starting from the identity element to define an exponential map. Okay, well, we take a left invariant vector fields, which are dual to left invariant one forms. You do a calculation with your with the Hopf integral, and you find out conveniently that the divergence is actually equal to 0. So if we forget the divergence, we simply solve our vector field equations in the first line of that proposition, nabla equals 0, as it says in the corner of the board. And we find this equation for the exponential starting at the point M in the Hopf algebra. Oh, and this is an element of the dual. So if I apply that to A, I get X of S of A1 dA of 2, which is an invariant vector field. So this pairs with an invariant vector field. That's actually just an exponential as a power series in the dual Hopf algebra. So we can solve this for some nice random Hopf algebras. Well, let's take the Hopf algebra functions on Z. Now, this will have a finite difference calculus. To keep it a star calculus, we'll have a move left one and a move right one element, and you insist that that's real, and you start it off at 0, and you get, well, the two things here, and they're surprisingly different. They're both evolutions of states on the time evolutions of states on the integers. The second one is rather more known. It's just the standard Laplacian divergence. Well, it's the heat flow for the standard Laplacian. And the exponential map looks much more exciting. It's certainly, well, despite the fact it's positive, it's trying to look oscillatory. And curiously, these things are actually given by the same hypergeometric functions, but you just insert an I in a couple of places. And that tells you what the difference between these things are. You can calculate it on the Hopf algebra S3, which again is given by a differential calculus specifying the 3 transpositions, and it just shows some starting values. And we may as well do it on quantum SU too, because there's slight problems with starting values here, because I'd really like to start at a delta function at the identity, but my analysis is certainly not up to that. So I started at just some random distributions given by A, B, C, and D. And that's the results of the flows there. Now, well, what's an exponential map for? Well, classically, the theory of Lie algebra says, you know Lie algebra, then you know the Lie group. Okay, add in simply, you know the simply connected Lie group. Basically, you can calculate everything. Now, unfortunately, this does not seem to work for Hopf algebras. You can do a lot of it. You can have the tangent space at the identity element, but it's, well, there's an interesting lot of problems you would have to go through to try any sort of classification procedure, and there's almost certainly quite a bit of additional information that you would have to put in. But it's an interesting problem to think whether you can actually get nice information about the Hopf algebra out of essentially it's a Hopf-Lie algebra, which exists in, well, considerable generality. You don't even need bicovariant things, although you get nicer formulae in the bicovariant case. And okay, I think, am I right in saying I should be thinking about stopping? Ah, okay, yes. So I shall just end this up with the importance of being a positive. Okay. Right.